Jai Hind everyone. I am Ankita Sharma. I am an assistant professor in AKGEC Engineering College. So today we will be covering our first topic, microprocessor of microcontrollers, 8085 architecture, the complex topic lecture number 1. So first of all, what is a microprocessor? If I talk about microprocessor, what is a microprocessor? So microprocessor is a programmable device that takes in instructions and numbers, performs some arithmetic and logical operations on that according to the program which is already stored in the microprocessor in the memory, and produces other number as a result in conjunction with the clock. So if I talk about the clock is simply a signal that is generated to some device so that the device can work. So what do you mean by a programmable device? The microprocessor can perform different sets of operations that might be arithmetic or logical operations, and we can change the program in different ways. So we can store the data, we can feed the data in the microprocessor, and we can manipulate it. How it is possible? We can get the data from the input devices. We can get the data if it is stored inside the microprocessor, or we can get the data from the outside world, and there are some devices which represent through which we can just input the data, such as keyboard, mouse and switches. So instructions, each microprocessor is designed to execute a specific group of operations. Suppose we have to add some numbers. For that I need an instruction of add, and I have to subtract two numbers, then I need an instruction of subtraction. So the group of operations which are used to perform some particular operation, the group of instructions, it is the instruction set. So instruction set defines what the microprocessor can and cannot do. The numbers, if I talk about the numbers, the microprocessor has a very narrow range, narrow view on the numbers. It can only understand the binary numbers. What are the binary numbers? 0 or 1. A binary digit that we have studied earlier also. Binary digit is called a bit, which comes from the binary digit. B from the binary, and from digit it's bit. The microprocessor recognizes and processes a group of bits together, and likewise a byte. A byte is combination of 8 bits. Word 16 bits. Double word will be 32 bits, and so on. So majorly in microprocessor 8085 we will be dealing with byte and word. Now how the microprocessor works? The microprocessor simply follows 3 sequences. The first one is fetch. It will fetch the instruction, it will decode, and then it will execute. Initially the instructions are stored in the memory in a sequential order, and the microprocessor fetches those instructions from the memory, decodes them and executes them regarding some operations or some instructions which it will get till the stop instruction. Till the stop instruction is reached, the microprocessor will stop working. We will get to know that halt or stop, they both meant the same. Later it sends the result in binary to the output port, and the output at the output port also, and internally the microprocessor will save that result in the accumulator as well. Between these processors, all these processes, there are some registers that store the temporary data and perform ALU performances also. So this is a micro-based system. Basically microprocessor is made from these 3 units. The arithmetic and logic unit, which is used to perform some arithmetic and logical operations, like we had discussed earlier as well, like AND, subtract, logical operations like AND, XOR, XNOR, ORing, all these logical operations. Control unit will control the nature, the behavior of the data which we are getting, and array of registers. The array of registers mean the group of registers which we use to hold the data, which microprocessor use to hold the data. So this is the basic diagrams for basic block diagrams, we can also say that, to just understand the working of the microprocessor. We have a microprocessor. If we have a processor, then there must be some input from where we are getting that input. Suppose I am getting this input from some keyboard, we can say that. This keyboard will, through this keyboard, the user will just input the data. The microprocessor will process that data according to the instructions that are already there. Through that memory, it will take the address, it will take the data, whichever it is needed, and then the output will be displayed in some LED or display. Further, this is a detailed block diagram for the microprocessor. What is happening exactly inside the microprocessor, we can get to know from here. There is an ALU, arithmetic logical unit. Register array is the group of registers. We can say register array is a group of registers, and there are number of registers in microprocessor 8085. There are general purpose registers, there are special purpose registers. So these all registers will make a group of registers, or we can say that register array also. So now there is a system bus. What is a system bus? System bus basically just take the data or the address from one place to some another place. So system bus is used to transfer the data. So in system bus, it is connected through all the devices, through all the possibilities from where the data can travel. The system bus is connected with input output, it is connected with memory and ROM, it is connected with the control register array and all these things. Now memory is of two types here, RAM and ROM. ROM, you all know, is a read only memory, only reading option is provided here. We can just read only from this memory. And RAM, it is used for dual purpose. We can read and write as well. So we can call it as read write memory as well. The random access memory will also be called as the read write memory. So next is our control unit. Control unit have different multiple signals which are used to control. It is the brain. We can say that this control system just controls the microprocessor. It is the brain of the microprocessor. It controls all the signals, from where the data is traveling, which signal will be converted into, which signal is which signal is generated here, and from where the instruction we have to move. So next is the microprocessor 8085 architecture, which is our topic. So microprocessor 8085, it is an 8-bit microprocessor which was designed by Intel in 1977. It is based on NMOS technology and it has following configurations. The data bus is of 8-bit, the 16-bit address bus, the address bus is of 16-bit. So what do you mean by 8-bit data bus and 16-bit address bus? 8-bit data bus means the maximum range of data which can travel from microprocessor 8085 is 8 bits. Suppose we have these bits. These 8 bits can travel simultaneously, can transfer simultaneously from microprocessor. It can process these 8 bits. And if I talk about the address bus, and one more thing I want to add on in data bus, the data bus is from AD7 to AD0. This is the data bus. We can say lower order address bus also, that I will be discussing lately. Now 16-bit address bus, A15 to A0. This is our address bus. So address is of 16-bit and data is of 8-bit. So what is 64 KB? So the memory of the microprocessor is that how many memory locations are there, how many memory locations are there in microprocessor. So 64 KB, we got it from here, 2 raised to power n. So here n is the number of address lines. In 8085 microprocessor, we have 16 address lines. So it will be 2 raised to power 16 The exact number will be 65536. These memory locations are there in 8085 microprocessor. And further, we can note it down as 64K bytes. The memory which 8085 microprocessor can hold. It can hold up to 64 KB. B is here byte, kilobyte. So 64 KB will be kilobyte. Next, it has a 16-bit program counter. Program counter basically is a counter which stores the address of next location which the microprocessor have to execute. Suppose the microprocessor have to pick the data from the location 2005H. Suppose our data is at this position, this location 2005. How will microprocessor got to know about this location? Is there any way? Will he remember the address? No. The program counter will do this for the microprocessor. The program counter will basically just store the data, location, the address for the next instruction from where the microprocessor have to execute. The next instruction which have to execute. Next is stack pointer. 16-bit stack pointer. What is a stack pointer? Basically, stack pointer runs on a function of push and pop. Two functions are there for stack pointer. We can push the data in the stack pointer. It will decrement by 2 at that point, and when we will pop the data, pop means we'll pick up the data from that, we'll pop it out, it will be +2 increment. So the stack pointer is also of 16-bit. Now there are 6 8-bit registers. In microprocessor 8085, there are 6 registers. 8085, there are 6 registers that are B, C, D, E, H and L. The data bus is also of 8 bits and the register is also of 8 bits. Here there are 6 registers, B and C. We will talk about B and C only. So B and C, these both registers 8-bit each, and all the registers C, D, these all are 8-bit each. So the microprocessor has 6 general purpose registers. All these registers are of 8 bits. Why? Because the data bus is also of 8 bits. That means 8 bit of data can be stored at once in 8085 microprocessor. But if I have to store the location address, then what? These locations are of 16-bit. The program counter was having the location 2005H. This is a lower nibble 8 bits, higher nibble 8 bits, or we can say that. So this 05, one register can store it, but what about the other one? 05 can be stored easily. What about the 20? So when the microprocessor have to store 16-bit address, at that time register pairs will work. Register pairs will work means the microprocessor has 3 general purpose register pairs, B, C, D, E and H, L. These 3 register pairs are pre-decided. We cannot mix them like B or D can make a pair. No, B and D cannot make a pair. B will be pairing with C only, D will be pairing with E only. Likewise, H is also pairing with L only. These are pre-decided. Nobody can change these. So we have to store a 16-bit data. At that time, we'll be using the register pairs, either BC, DE or HL. So now we can store the 2000 H data at 2005, sorry, data at B and C. C is the lower part of this register and this is the higher part of register. So if I look in 2005, in 2005, 05 is the lower order address and 20 is the higher order address. So that's why this 05 is stored in register C and 20 is stored in register B. Next, it requires plus 5 volt supply to operate at 3.2 megahertz single phase clock. This is the clock frequency and the power supply which microprocessor requires for the working. And what are the uses? Where is the implementations for the microprocessor? The microprocessor is a general purpose device. It is used generally, not for a specific purpose, like in microcontrollers. Microcontrollers are used for some specific application, like in our some robot we have to make, then you have to just use that microcontroller for that particular use. So in washing machines, generally, microwave ovens, and in our mobile phones also. So this is the block diagram of 8085 microprocessor here, which we have discussed here also. There is a multiplexer. There are two registers, W and Z. These two registers are general purpose temporary register. These are temporary registers. These are our microprocessor has two temporary registers, 8-bit each, W and Z. And these 6, which we have discussed just now, B, C, D, E, H and L, these all are 8-bit each. The bracket here denotes the number of bits. So B, general purpose, 8 bits, C also, D, E, H, L. Next is stack pointer, it is of 16-bit. Program counter, it is also of 16-bit. And next is increment and decrement and further address latch. Now what is increment and decrement? Increment and decrement is like if I have to take the next location, suppose program counter is having this location. This address is stored in program counter. So then what will program counter do? The microprocessor will pick this address and will execute it, right? So this at this address, whatever the instruction, whatever the data is there, it will be executed by the microprocessor. Now what? The program counter must need some instruction so that it can increment. For that we use increment. Suppose the microprocessor, the program counter will have to store the next location. It will be 2006. How it is possible? It is used by increment. And if we have to do decrement, it will be decrement by 1. The decrementer will be used for the stack pointer. Next is our address latch. Address latch is used for the address and data buses here. So data bus was of 8 bits and address bus is of 16 bits. So these are address and data bus. One more thing I just want to discuss here, address and data buffer. Here, address and data bus. Address and data buffer contains the address and data bus. If you see here, AD7 to AD0, and in higher order bus, it is A15 to A8. The higher order address bus is independent from any other bus. It can carry the higher order address, the higher order part of that address, but address and data, these both buses are demultiplexed. These are multiplex, sorry. These are multiplex, these are, we can say, time shared. So these pins will be shared by address bus and data bus. Which pins? AD7 to AD0. It will just time share it. We will be discussing this in our next lecture. That will be a special topic, separate topic of demultiplexing, how this is done. So now next is our serial input output control. It is this group is used for serial data communication. It is used for serial data communication. If the microprocessor is communicating with some other peripherals like input output peripherals, then this pin is needed, then this group is needed, and further there are two pins, SID and SOD. SID is, one is SID, second is SOD. These two pins will be discussing in our next lecture. This is serial input data and this is serial output data. So here this is our register group, we can say. This is our register group. This is our address data buffer. This will be our this group. This group is instruction register, decoder and timing control group. This is our arithmetic and logical group, and this is our interrupt control group. So we talk about interrupt control group. This is used for dealing with the interrupts. In microprocessor, there are number of instructions, or number of interrupts that the microprocessor have to deal with. Some of them are trap, RST 7.5, RST 6.5, RST 5.5, INTR and INTA bar. These both are generally signals. INTR is basically the interrupt request that will be discussing in detail in the pin diagram. So here these are interrupt pins and this is an interrupt acknowledgement signal. When the microprocessor has acknowledged the interrupt request, then this pin is generated. Accumulator is also a register. It is of 8-bit register. All the data, all the result. Suppose we have done the arithmetic and logical operation between two registers, then the one register is fixed and that is that is our accumulator. So this accumulator will store the result also of that operation. Suppose we are adding two numbers, one number is stored in some register. Suppose we take register B. Register B is having one number and accumulator is having the another number. These two numbers will add when the microprocessor will get the instruction add. These two numbers will be add and the result of these two instructions will be stored in the accumulator itself. So the next is temporary register. It is a microprocessor's temporary register. It is not user friendly. It is not for users. Only microprocessor can use this temporary register, and here it is flags and flip-flops. It is also of 8 bits. There are simply 5 flags in 8085 that we will be discussing right now. So this is a timing and control. Timing control, we have clock, generation signal, clock out, ready pin, read bar, write bar. RD bar is read bar, write bar. ALE is address latch enable. S0, S1, these are status signals. Input output memory bar. Hold and HLDA, these are DMA signals. DMA is direct memory access signals. And reset pins, we have two reset pins, reset in and reset out. So this is the functional diagram for the microprocessor. Accumulator, it is an 8-bit register which is used to perform arithmetic logic, input output, load store instructions, and it is connected to internal data bus and ALU as well. Arithmetic logical unit, it is used to perform arithmetic and logical operations like addition, subtraction, and or etc. on the 8-bit data. General purpose registers we have discussed earlier. Also we have 6 general purpose registers, B, C, D, E, H and L, and these registers can work together and make a register pair to hold the 16-bit data, and these pairing combinations are these, and these are fixed. These pairs are fixed, B, C, D, E, H and L. So next is program counter. It is a 16-bit register which is used to store the memory address location of the next instruction to be executed. The microprocessor increments the program whenever an instruction is executed. So program counter will just point to the next instruction which the microprocessor have to execute. So the stack pointer is also 16-bit register word like stack, which is always incremented or decremented by 2 during push and pop. Why 2? Because it is of 16-bit, and in microprocessor 8085 the memory can hold up to 8-bit of data. So if we are just popping 16-bit data, it will be decremented by 2, and if we are pushing, then it will be decremented by 2, and we are popping, it will be incremented by 2. Temporary register is also an 8-bit register which holds the temporary data of arithmetic and logic operation. Next is our instruction recorder and instruction register. It is also an 8-bit register. When an instruction is fetched from the memory, then it is stored in the instruction register. Instruction register will just keep that instruction in its to store in it. An instruction decoder decodes the information which is present in the instruction register and further passes it to the ALU. So these are the flag registers which we were talking about. Here we have 5 registers. We have 5 flags. It is an 8-bit register, and we have 5 1-bit flip-flops. It will either hold 0 or 1. So different flags or different flip-flops we have is sign flag, 0 flag, auxiliary carry flag, parity and carry. So these flags will be set or reset according to the result. So sign flag is used to indicate the data, sign of the data in the accumulator. Suppose we are doing a subtraction, and if the subtraction is like A minus B and A is 30 and B is 40, the result will be negative. Then the sign flag will be active. Next, 0 flag, if the whole result is 0. If whole result is 0, suppose we are doing this 0, 5 minus 0, 5, the result will be, at that point, the 0 flag will be 1. Next is carry flag. If we are doing some addition or subtraction, or if some carry or borrow is occurred from the arithmetic operation, after some arithmetic operation there is some borrow or some carry, at that point of time it will have carry 1 or borrow 1. Next is auxiliary carry. Suppose we are adding 2 numbers. We are adding these 2 numbers 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, carry 1. So when the carry travels from bit 3 to bit 4, lower nibble to higher nibble, or we can say lower nibble to higher nibble, the carry generated between this is the auxiliary carry. So the carry here, it is the auxiliary carry. So if we complete it, 0, carry 1, 0, carry 1, 0, carry 1, 0, carry 1. So if we have to find out the number of flags, which flag is active, which flag is not active for this, just check it, we will check it here. What will be the parity? Now, what will be the sign flag? The sign flag is 0 because the result is positive here. 0 flag is 0 because the answer is non-zero. It is 4 and 0, and there is one carry also. So next is auxiliary carry flag. So auxiliary carry flag is this carry. If this carry is generated from lower nibble to higher nibble, if a carry is generating, then this carry is auxiliary carry. So for particular this example, the auxiliary carry was there, so it will be 1. Next is our carry flag. If the result is having a carry, like here, there is one carry in last, then the carry flag will be active. If there is no carry, then there will be 0. It will be reset. So we can say this is reset, reset, set and set. Now the last is the parity. Parity means the number of ones in the result. This is our result and the total number of ones. If the number of ones is even, if the number of ones is even, then it will be set, means 1. Then the parity will be 1 and parity will be 0 if it is odd. So here the number of 1 is odd. So the parity is 0. Why? It is odd ones. So some of you may ask that the even number 0 is also an even number. Then in that case what will happen? In case of 0, it will be 0 because we have to count the number of ones. 0 might be an even number, but we have to count the number of ones. If the number of 1 is not there, suppose the answer is 0, all the bits are 0. In that case, the parity will be 0. Timing and control unit, it provides a timing and control signal to the microprocessor to perform following instructions. These are control signals: ready, read bar, write bar. ALE is address latch enable. We will be discussing all these pins in the pin diagram in detail. S1, S0, IO, M bar, input output memory bar. These are status signals. Hold and HLDA is our DMA signals. There are 2 reset signals that are used to just reset the microprocessor. These are reset in bar and reset out. Now what is an interrupt control? When a microprocessor is executing a main program and whenever the interrupt occurs, the microprocessor shifts the control from the main program to process that particular operation, and there are these interrupts. Serial input output, the serial data communication, address buffer, we have discussed earlier, AD7 to AD0 and A15 to A0. These are our address buses. The data bus is bidirectional, but the address bus is unidirectional.